So in this demonstration, we will study the gamma ray spectroscopy using multi-channel analyzer. So this is the actually block diagram for MCA. So here also you are using the scintillation detector, then you have a high voltage unit, linear amplifier, and your MCA, and this MCA output is connected with the PC. So make the interconnection as per actually this the block diagram, and you switch on the PC and also the gamma ray spectrometer. Place the cesium 137 radioactive standard source at a distance of 4 to 5 centimeter from the face of the scintillation detector, and then set the HP value, means high voltage value, around on the instrument at operating voltage that you calculated when you perform the AC analysis. The same operating voltage you set here in the scintillation detector used for this experiment. Then you can actually accumulate the cesium 137 spectrum in the using the ONUSPECT software. So here actually in the desktop we have the ONUSPECT icon. You just double click, so you will get this one. You just click this one, then the ONUSPECT will appear. Then once you will get the main screen, and they will appear at the start. You just click the online analysis. Once you click, then this screen will appear. You can see here. Then here you set the timing at 100 seconds. That is enough, normal second in enough to get the good photo pic. Once you set, then you click the start. This one you click. This is the spectrum marker. Start the spectrum. Then there is a appear icon that device opens. Also you click. Then it will appear, the spectrum will start. So you wait for 100 seconds. Then adjust the amplifier gain. Here you adjust the amplifier gain such that that photo peak of 662 keV gamma of cesium 137 will appear at approximately at channel number 300. So you can see in the spectrum, so x-axis your channel number and y-axis you are getting the counts. So you are getting the entire spectrum on the screen. So you adjust the gain such that at channel number 300 you will get the photo peak. So you wait for you can wait for 100 seconds. Then once the time over, so entire spectrum will get. So now you will get the spectrum like this. Then you click the OK. So now this entire spectrum you have to save. You right click, then you click the save spectrum as. Then once you get, then you go to the desktop. You some name you put, file name you put. Let's say we are putting the file name. You save the file somewhere in the desktop. Then you go to the file and you click the spectrum, and you import the spectrum where you saved, and you open it. Then load previous calibration, click no. Then spectrum will come. Now we have to analyze the spectrum. So then first we will go to the pictures. Then you click the right click, then ROI selection you do, then add ROI, then you bring this one to the near to the peak. Yeah, so this way actually your ROI means region of interest that report will generate. That actually will give you the entire information like full width, half maximum, gross count, net count. You can get all the information about this photo peak. Actually, the full width at half maximum is the channel width of the cesium 137 spectrum at the half peak height. From the ROI report, you can see that full width half maximum, and the resolution of the NI scintillation detector is defined as the ratio of full width half maximum divided by the peak channel. So now how to select the photo peak? So for that, go to the source, then full earth have calibration needed for multiple, then you calibrate, then you right click, then input text box, go to, then here you write the value, let's say 6162, and you drag it to the near this peak. Then you calibrate. So now you can see the channel is actually the channel is converted to the energy in keV. To study the cobalt 60 spectrum and calculation of resolution of the detector, you have to follow the same procedure as we do for the cesium-137. To study the behavior of the gamma ray spectrometer with different energies of gamma sources, place different energy sources on the detector 2 cm away. Minimum, let's say 3 energies are required for energy calibration. We are placing 3 sources here around 2 cm away. You have to keep the sources very carefully. So you have to keep the sources like this. Once you keep, then you switch on the power supply, and also you fix the operating voltage. So now keep the time, let's say 500 seconds. Then you start it. Device also okay, make it. Then wait for 500 seconds. So now acquire the spectrum, and to get a fine spectrum, then you have to save it. So go to the save spectrum, right click, then give the file name. So again the file name, and save it. Then go to the file menu, spectrum, click spectrum, and import the file. Load menu, you click no. Then once you get the spectrum, you go to the peak source, right click, then go to ROI selection and add ROI. So let's say this is my first peak, we select over there. Then again add ROI for the second peak. Then this one, so let's say this is the third peak. Because 3 sources we have taken. So once you do add ROI, and here also 4th peak of the cobalt. So cobalt we are getting 2 peaks. Then you go for the peak source. Then okay. The screen will be acquired. Then you go for calibrate. Once you go to calibrate, then right click, input text box you click, and then you write the value for different actually energy value of different sources. For the gamma you write 6162. So place over here. Then for, let's say, barium, write 356 over here. Then for cobalt we have 2 energies, 1172 and another is 1335. So you place over here. So once it is over, then calibrate. EKFA, then show the polynomial, and this is actually plot draw between the energy and the channel as shown in this figure. And you can actually get the unknown energy of the radioactive isotope also. For a mass absorption coefficient experiment, we are using aluminum sheet. Our total 12 pieces we are taking, each of 0.5 centimeter. So you can place at a time one by one over here in between source and the synthesis detector. So adjust the amplifier gain so that the photo peak of 662 keV gammas will appear at approximately channel 300. So here you can set the timing, let's say 100 seconds. So give the time here 100 seconds. So once you give, then insert the first piece of the aluminum observer, which is 0.5 centimeter thick, which is already placed in between the source and detector. So now you acquire the spectrum. So, and you can repeat the additional pieces of aluminum observer in an increment of 0.5 centimeter until the gross area under the 662 keV photo peak falls up to, let's say, 2000 counts. Acquire spectrum for each thickness of the aluminum observer. You also obtain the background spectrum for the let's say time for 100 or 150 seconds, and you have to take the ROI reports as per the previously we have shown in case of cesium-137 sources, and for the respective observer thickness. From the ROI report, obtain the gross counts pertaining to 662 keV peak against each observer thickness, and obtain the gross background counts from the ROI report pertaining the background, and then calculate the net counts for each observer thickness. So net count is nothing but your difference between gross count and background counts. Then tabulate the data, let's say as per shown in the table, and you plot the net count versus the observer thickness. So you will get the plot like this. So that shows the variation of counts with the aluminum observer thickness. So this is from this actually you can calculate the graph. Actually you calculate the mass absorption coefficient of the aluminum. Thank you.